Hey guys, my name is Iman and welcome to my presentation on TEMS. TEMS stands for Transparent Energy Modeling System, and it's a MATLAB toolbox developed to solve economic dispatch problem. Economic dispatch is basically finding the optimum generation mix that meets the electrical load at the lowest operating cost. Economic dispatch can be formulated as a constraint optimization problem where we try to minimize the operating cost with respect to many constraints such as maximum generation capacity, maximum ramping capability, water limitation, and so on. Please check out the documentation for TEMS to see the way that we have implemented the optimization problem. In this presentation, I'm going to explain the features in the current version of TEMS, and then I will show you 3 examples on how to work with this toolbox. Let's start with the generation. You can define 4 types of generation. The first one is a thermal unit, which is endogenously defined in the model. The second type is the one with exogenously defined profile, such as wind and solar. The third one is market, where the user defines different offered quantity and offered price. And the last one is a cascaded hydroelectric system, where you can cascade as many reservoirs as you want. Also, you can define DC transmission lines using TEMS. Basically, all you need to do is to click to create nodes and then click on 2 different nodes to create a transmission line. It's very easy. I will show you how to do that in the second and third examples. Inputs or variables defined by the user can be either static or a pattern. For some inputs, it doesn't make sense to have a pattern. For instance, maximum reservoir capacity is not going to change over the time and must be a static number. Okay, let's solve 3 examples to practice how to work with TEMS. In the first example, there is just one node and therefore no transmission line. We have a thermal unit, wind farm, solar farm, and a hydro unit with just one reservoir. Wind and solar profiles are exogenously defined for the model. Let's look at the code. There is one node and the name is A. Wind and solar, as I said, are exogenously defined in an Excel file. So we need to read data and store it in wind profile and solar profile. The simulation horizon is 24 hours. COLL is the cost of lost load, and it should be the largest cost or penalty in the system. COE is the cost of excess generation. COS is the cost of a spillage or releasing water through the waterway, not the generation dam. I will explain this in the next example. COT is the cost of transmitting power over a line. Electrical load here is static over 24 hours. For the thermal unit, we need to define short-run marginal cost, maximum generation capacity, and maximum ramping capability. Also, we need to tell the solver which node this unit belongs to. And here's an optional name for the unit. Don't worry about the rest, this is basically housekeeping stuff. Let's move on to the wind farm. I defined a negative number for the short-run marginal cost to set it as must take. Here is maximum generation capacity, and then I need to define the profile for MATLAB, which is exogenously defined. This unit belongs to node A, and here's the name. For solar, SRMC is -2, so the solar generation is the first priority for the solver. Maximum capacity is 50, and here's the profile, node, and the unit name. For hydro units, we need to define short-run marginal cost, maximum capacity for the dam, natural inflow into the reservoir, maximum reservoir capacity, initial capacity, water recovery factor, which is a number between 0 and 1. 0 means the solver can use the whole water in the reservoir. 1 means the water level at the end of simulation must be equal to the beginning. Okay, we are done. TEMS will take care of the rest for you. Let's run it. Done. TEMS enables you to quickly see the results. For example, let's look at the generation from all the units and let's set the presentation format to a stacked bar. Also, you can look at the load for each node. As you can see, there is no thermal generation in this case as cheaper options are available. Let's look at the water trajectory or water level in the reservoir. As we set water recovery factor to 0, the solver is allowed to use the whole water available in the reservoir. Also, hydro spillage is the water released through the waterway. As you may remember, I assigned a cost called COS or cost of spillage to this water release. Therefore, TEMS is not going to use it unless it has to. Finally, you can see the curtailment for wind or solar. Now let's set the water recovery factor to 1 and run it again. Let's look at the generation and load. As you can see, we have thermal generation in this case because the water level at the end of simulation must be at least equal to the beginning, and we cannot use the whole water. Here is the water level in the reservoir. As you can see at the end, the water level is equal to the initial value, i.e. 300. Now let's set the maximum thermal ramping to 1 and run it again. As the thermal unit cannot ramp up or down quickly, it must be available all the time to deal with wind and solar intermittency. Finally, let's make the natural inflow 10 times larger and run it again. In this case, because there is too much water in the system, the solver needs to spill the water through the waterway. Otherwise, the water level goes beyond the maximum reservoir capacity. As we have lots of water in the system, we can turn off the thermal unit all the time. Also, water level stays at 300 as water inflow into the reservoir is larger than the water outflow from the dam. Let's move on to the second example. In this case, there are two nodes which are connected with a bidirectional line. There is a market in node A. For the first 100 MW, the price is 3, and for the second 100 MW, the price is 4. Also, there is a market in node B. For the first 50 MW, the price is 2. For the second 50, the price jumps to 5, and for the last 100, the price is 10. Also, in node B, there is a cascaded system with two reservoirs. Water can go from the head to the tail either through the generation turbine or through the waterway. In general, we don't want to release water through the waterway because we can save it in the reservoir and use it later for power generation. That's why TEMS assign a cost for using waterways. This cost is called cost of spillage or COS. So the solver is not going to release water through waterways unless it has to. In this example, we define the load for node A and B exogenously. Let's see the MATLAB code. There are two nodes. Load for node A and B are exogenously defined in an Excel file. So we need to read data and store it here. H is 24 hours and other costs are the same. Here I define the electrical load for node A and B. For the first market, we have two bands. Here is the offered quantity and here is the offered price. This market belongs to node A, and here is the name. For the second market, we have three bands. This market belongs to node B. For the cascaded hydro system, we need to define short-run marginal cost, natural inflow, reservoir capacity, initial water level, and the water recovery factor for two reservoirs. This unit belongs to node B, and let's call it hydro. Now let's run it. We need to define two nodes and one transmission line. So click twice at two different locations to create two nodes, A and B. Here we go. Then, to create the transmission line, click on node A and then click on node B. In these boxes, you can define the line capacity from A to B and from B to A. 200 MW is good, so press OK and close this window. Here is the result. First, let's look at the generation and load in node A. As you can see, we still need another 100 MW for the first 12 hours. Either solver needs to import power from node B to A to satisfy the remaining load, or there would be a lost load. Here is the power flow from node B to A. So the residual load in node A is met by generation in node B. Now let's look at the generation and load in node B. For the last 12 hours, we still need another 100 MW to meet the load in node B. So node A generates 100 MW and send it to node B through the transmission line. Also, let's look at the water level. The water recovery factor for the first reservoir is 0. That's why the solver used the whole water. For the second reservoir, this factor is half. That's why the water level at the end is almost 50, which is half of the initial value. Now let's set the line capacity to 50 in both directions. In this case, the load cannot be fully met by all generations in node A and power flow from node B to node A. The power flow cannot go beyond 50, which is the line capacity. So we end up with 50 megawatt unserved load in node A. The same situation in node B. As the maximum capacity for the transmission line is limited to 50 megawatt, we end up with unserved load. Now let's move on to the third example. Here we have 5 nodes. A is connected to B with a unidirectional line. A is connected to C with a bidirectional line, and the line capacity is different in each direction. C is connected to B with a unidirectional line. C is connected to F and D with bidirectional lines with the same capacity in both directions. In node A, we have thermal and wind generation. In node B, we have a thermal unit and a cascaded hydro system with 3 reservoirs. In node C, we have market and thermal generation. D has just a market and F has just a thermal unit. The natural inflow to the first and second reservoirs, load, wind profile, and short-run marginal cost for the thermal unit in node B are all defined exogenously. Now let's look at the code. There are 5 nodes. This is the exogenous data defined in the Excel file. So we need to read data and store it here. The load pattern is the same for all the nodes, but each node has a participation factor, or basically has a weight. For instance, the load in the first node is 30% of the total load, or in the second node, it's 15%. Here's the thermal unit in node A. Here's the wind farm with the profile that is exogenously defined. Here's the thermal unit in node B. Here's the cascaded hydro system. We need to define generation cost for 3 dams, maximum capacity and natural inflow. Natural inflow into the first and second reservoirs are exogenously defined patterns, but for the third one is 0 all the time. Here is full reservoir capacity, initial value, and water recovery factor. The next unit is thermal generation in node C. Also, there is a market with 2 bands in this node. There is another market in node D with 4 bands. Finally, here is the thermal unit in node F. Now let's run it. First, we need to define nodes and transmission lines. So click 5 times at different locations to create 5 nodes. Here we go. To create the first transmission line, click on A, then click on B. The line capacity from A to B is 100 and from B to A is 0, as the line is unidirectional. The second unidirectional line is from C to B and the capacity is 50. The third line is from A to C and it's bidirectional with different capacity in each direction. The next line is from C to F and the last line is from C to D. Close the window and here's the result. First, let's look at the water level for the 3 reservoirs. The water recovery factor is set to 0 for the first reservoir. That's why the solver used the whole available water. For the second reservoir, the factor is 1/2. That's why we end up with 50, which is half of the initial value. The recovery factor for the last reservoir is 1, so the water level needs to be at least equal to the initial value, i.e. 100. If water can be saved in the reservoir for later, the solver will definitely do that, as there is a cost associated with releasing water through the waterways. Now let's look at the generation and load in node A. As you can see, there are some hours that generation goes beyond load, which means this node exports power to other nodes through the transmission lines. For instance, here's the power flow from node A to node C. Let's look at generation and load in node D. To meet the load, more power is still needed, which must be imported from other nodes. Node D is connected to C. So let's look at the power flow from C to D. Node C cannot provide more as it needs to meet its own demand. So the residual load in node D is basically unserved load. Okay, that's all I want to say. Thanks a lot for watching this video. If you have any question on TEMS, please type it in the comments section below. Also, if you're interested to see more stuff on planning for energy systems, please check out the homepage for our research group called 2060 Project. This project is at University of Victoria and funded by Pacific Institute for Climate Solutions. To find more, just Google 2060 Project and the first link is our homepage. Also, please follow us on Twitter at 2060 Project to see the latest research findings. Thanks again and see you guys in the next video.